Hello students, today we have assignment 4.2. Last time we had Ostier's experiment, his observation and Biot's law. We also saw first application of Biot's law, that is how to determine magnetic field due to straight current carrying conductor. Today we have two more applications of Biot's law. First is how to determine magnetic field due to current carrying ring. So we'll consider a ring which is carrying current, and we'll see how to determine magnetic field at some point on its axis. And then we'll have special cases, three special cases for ring. Next we'll determine magnetic field due to current carrying solenoid. So we'll see what is solenoid and how to find out magnetic field due to solenoid. And there we have four special cases. So mainly two topics we have today. So let us start. I'm sure you remember, but let me yet remind you again that Biots law says that dP is mu 0 by 4 pi IdL cross R by R cube. What is mu 0? It is permeability of vacuum. What is ITL? It is called current element. And what is R? R is the position vector of the point where we want to find out magnetic field with respect to ITL. Okay, so very first condition to determine magnetic field using Biots law is we must have IDL, that is current element decided, and next is find out R, and then we can use this formula to determine magnetic field. So we'll proceed the same way as we did in previous video session. So let us start. We'll start with concentration. What is the concentration? Now we have a ring which is carrying some current, and let us consider that there is some point on its axis. Okay, so what are the parameters here we have to decide? So I will consider that the radius of the ring is r, and let the current be passing in this fashion. Say current is I. Okay, where you want to find out magnetic field? I want to find out magnetic field at some point which is here. You may label it as P or X or Y or whatever. So now, what next? Next is I'll have to decide what is ideal. So in this case, let me consider some ideal here. Say here is my ideal. Okay, so this is my chosen ideal. And with respect to this ideal, where is the point? So I would say that the point is at say distance r. So let it be r. Okay. Now, if you apply right hand screw rule, you realize that whenever you take A cross B, suppose if I take A cross B and if resultant vector is C, one thing I can always be sure of about C is that C is always perpendicular to A, C is always perpendicular to B. So the three, C will never be coplanar. It will not be on the same plane as that of A and B. Examples are I cross J. What is I cross J? K. Okay. J cross K. What it is? I. So resultant in case of cross product is always perpendicular to the two component vectors. So here also, if my ITL and R both are as shown in figure, where is the next vector? That is the dB. So dB would be somewhere here. Suppose this is dB. Now for this dB, I can always define one component along the axis and other component perpendicular to the axis, isn't it? So if this is say angle phi, let this be angle phi, then this will be dp cos phi, and this will be dp sin phi component. Perpendicular component perpendicular to the axis is dp sin phi, parallel to the axis is dp cos phi. Now, in case of ring, you can always have one diametrically opposite current element, say here, uh, say this is IDL2, let the previous one be IDL1. So I can always have diametrically opposite current element whose magnetic field is like this. So if previously I have dB1, now I have dB2. And what is happening now? Sorry. So now for this dB, again, if I take component parallel to the axis and component perpendicular to the axis, look at the condition. If this is phi, it has to be phi because we are talking about the ring, so angle has to be same. So dB cos phi and dB sin phi, if I consider, what is happening here, these two are mutually equal and opposite. Okay, and what is happening with the parallel component parallel to the axis, these two are in same direction, so I'll have to add the two. And similarly, you consider any current element. Suppose if you consider some current element here, you can always find out opposite current element whose dB sin phi will be cancelled out. If you consider some current element here, you can always have another diametrically opposite current element whose dB sin phi will be cancelled out. So ultimately, you will be left with only cos component. And what is the advantage? What is the advantage of that? So advantage is, let me keep it aside. So now, if I consider resultant magnetic field, which is integration of dB, I don't have to worry about both components of dB. I just have to worry about dB cos phi. Now see, this is very much advantageous condition here because what was the case? We said that dP sin phi and dP sin phi are cancelled out. Which dP sin phi's are cancelled out? For such IDL, the IDLs which are diametrically opposite, they have their perpendicular components being cancelled out and parallel components being added. So when I am finding out resultant magnetic field, I don't need to worry about dB sin phi. Resultant magnetic field is integration of dB cos phi, and it is integration over the ring, so closed integration. Okay. So what is the formula now? So now I can write B as closed integration of mu 0 uh, by 4 pi. Now I still don't know the other terms. IDL r sin theta upon r cube. Okay, I'm writing only magnitude because now we know that the direction of the field is along the axis, so I'm not worried about direction part. But there is still one thing bothering me. What is that? It is this thing. What is sine theta? And from where it has come? See, we have IDL cross R in the Biot's law. Go back to the formula. See, here is the formula. So for any cross product, when you are writing only magnitude, so it is IDL R sine theta by R cube, isn't it? and some vector you will have to mention if you want direction, but in our case we know that the direction is along axis. The direction of magnetic field is along this axis dB cos phi, and so I am not worried about direction part. So now I want to know what is the angle between IDL and R. But here if you look at the situation, this IDL is coming out of the plane of paper and R is perpendicular to it, and hence theta value is 90 degree. Okay, this is the ideal direction coming out of page, and this is R. So what is the angle between IDL and R? It is 90 degree. And then my equation is reduced down to closed integration of mu 0 I by 4 pi. Now I don't need to write sine theta. Sine theta is 1. Okay, so sine theta is 1 for this case, and r by r cube will give me r square in denominator, so 1 by r square cos phi dl. Now look at the diagram. We have r constant, isn't it? Phi is also constant, so cos phi will be constant, and mu 0 and I, they are obviously constant terms. 4 pi is also constant. And then what we have, so if I take all the constant terms out, mu 0 I by 4 pi r square uh, cos phi dl. Okay, what is cos phi? So if you look at the diagram, you will see that this is radius of the ring. Okay, and let us consider that the point of interest, the point where we want to find out magnetic field, let it be at x distance. So this is r, here is x, and so we are talking about a triangle. We are talking about a triangle where we know three parameters. Okay, and this is pi by 2 minus phi. This is 90 minus phi. When you look at the geometry of figure, you will understand this is 90 minus phi, and then this angle will be phi. So what is cos phi? Adjacent upon hypotenuse, or else we can write it to be r by under root of r square plus x square. Okay, applying Pythagoras theorem. So then I will write my formula as mu 0 I by 4 pi r square r upon under root r square plus x square closed integration dl. What do you mean by closed integration dl? You will get circumference. When you sum up all the dl's over the ring, you will get circumference, and then it will be mu 0 I by 4 pi r square r upon under root r square plus x square into circumference, that is 2 pi r. Simplify it further. So I have 4 pi, I have 2 pi. So what I will be left with? Mu 0 I by 2. Okay. One more change I will make here. Say this r square is actually hypotenuse, isn't it? R, small r is hypotenuse. So r square is r square plus x square, and we have one more under root r square plus x square. So r is under root r square plus x square. What you will get if you multiply this to r cube, isn't it? So you will have r cube. You can write it two different ways, r square by r cube, or else you can write it as mu 0 I by 2 r square upon r square plus x square raised to 3 by 2. So here is the formula. B is mu 0 I by 2 r square upon r square plus x square raised to 3 by 2. This is the expression for magnetic field due to current carrying ring. Okay, so let us have a look at the answer. See, first of all, consider a ring of radius r and it is carrying current I. This is the figure. Okay, we are considering a current element, and then you have to show all this component vectors dp1, dp2, and dp sin phi, dp cos phi. Okay, and then let the magnetic field and current, you can have a look at all the statements. This is the derivation part, main step, that when you are finding out magnetic field due to ring, we don't have to worry about sign component, because sign component of diametrically opposite current elements are mutually equal and opposite, so cancelled out, and hence this is what we are left with. So what is happening to the sine theta? So as I told earlier, sine theta is angle between IDL and R, and theta is 90. So sine 90 is 1, and hence that factor is also eliminated, and this is where we reach. Substitute cos phi and simplify it, and this is the expression for ring. So that was the topic. Now let us go to special cases. So what are the special? Okay, one more thing I would like to remind you here is that whenever you want to determine direction of magnetic field, one way is to use right hand screw rule. So if you have a ring and suppose current is going like this, so what you can do is place a screw and rotate it in the direction of current. So if this is the current, this is how you can rotate, as shown here, and then you will see that the screw will advance in one direction. In this particular case, the screw will go like this. So you can say that this ring will have its magnetic field in left direction. Okay, magnetic field lines would come out from the ring in left side and enter into from right side. So the field of this ring will be like this. This is the nature of magnetic field of this ring. Okay, you can also compare it with bar magnet. See, if you take small bar magnet and if you take north pole here, south pole here, the magnetic field will be very similar. So you can say that the bar magnet and the ring, they are having some analogy, they have some similarity. Okay, second way to determine magnetic field is you can hold. See, what you can do is uh, take a ring and see in which direction current is passing. Okay, and hold hold the ring in such a way that your fingers are curling. Fingers are curling around the axis in such a way that thumb is along the axis, and then uh, sorry, fingers are along the current, and then thumb will indicate direction of magnetic field. And if you have straight wire, suppose this is straight wire, and here if you keep your thumb in the direction of current, then your fingers will indicate direction of magnetic field around the uh, wire. Bear with the drawing. So this is second way of determining magnetic field. I assume this is easier way, but there is one more. The third way says that look at the ring, and then if you see that current is going like this, then it indicates that you are facing south pole, means the magnetic field lines are going inside. But if you see that current is anti-clockwise, then it's like N. So the part you are facing is the part where field lines are coming towards you. Okay, so if current is like this, you should understand that field lines are coming out. If current is like this, you should understand that field lines are going in. So these are different ways of determining magnetic field due to current carrying ring. Let us move to special cases now. These are the special cases. First, magnetic field at given point on the axis due to current carrying ring with N turns. Very easy. What difference does it make if you have N turns? You say this is the formula. This is the formula. You just have to multiply it with N. So when you have N turns, put here extra N and you are done. Okay, this is the formula. There is printing mistake, you can correct. Add one N here, and this is the formula. The only condition here is X should be very greater than R. Okay, so number of turns should be very close. So if you have this kind of condition, suppose these are the turns, suppose I want to find out magnetic field due to these 4 rings at some point here, say point P. Now X here, X here, X here are not same, so I cannot use this expression. Okay, but if I have rings like this, suppose these are the rings, and then I want to find out magnetic field here. So for this rings, I can say that X is constant. Okay, and then I can simply multiply this equation 4.4.3 with N. So you can always multiply this with N and find out magnetic field due to N turns. Next is magnetic field at center of the current carrying ring. So at center, what do you mean by center? When you are at center, X will be 0, isn't it? Suppose I want to find out magnetic field at center. So what is the X value at center? X is 0, and then mu 0 I by 2 r square upon r square plus x square raised to 3 by 2. What if I take X to be 0 here? Take X 0, and what you will be left with? Mu 0 I by 2 r square upon r square raised to 3 by 2, that is r cube. So mu 0 I by 2 r square by r cube, that is mu 0 I by 2r. This is the magnetic field when you are at center of the ring. See, this is the magnetic field, mu 0 I by 2r, that is the radius. And if you are talking about magnetic field at some point, we don't have ring, but if you have only arc, now what to do? Suppose if you have arc, see, for complete ring, I can say that magnetic field is mu 0 I by 2r. So when I consider 2 pi, complete ring means 2 pi angle, magnetic field is mu 0 I by 2r. So if I have only part of the ring, suppose I want to find out magnetic field due to only the small part, arc of the ring, say this much arc, which is surrounding angle theta. So how much is the magnetic field at center due to theta angle of the ring? So that will be mu 0 I by 2r theta upon 2 pi. So this is the magnetic field due to part of the ring arc, you may say. So that is all for now. In next video, we'll discuss magnetic field due to solenoid. Thank you.